All right, good morning. Did you have a fun night yesterday? Too much fun? But as my conference friends like to say, we're not here for pleasure, so let's continue. Um, Freaking computers, how do they work? We'll try to answer this question today. Um, my name is Michał. I come from northern Poland, but I moved to Sweden some time ago. I work for Triton 37. Triton means 13 in Swedish, so it's sort of a joke going on. If you get it, you get it. We're a consultancy company, but our motto is creating value by sharing knowledge. We like not only to be like mercenaries paid by hour, but also leave our clients' project at better state than we see them when they get there. And we also do a lot of knowledge activities. We speak at conferences and stuff like that. So let's start about modern programming a little bit. The inspiration for this talk was some discussion with my colleagues that write high-level code, C# or JavaScript, and they're very productive doing like npming stuff or using NuGet, not even thinking how stuff works inside. And it's great. You can get very productive. You can get to write very good code. But sometimes the npm code that I like use packages that like for me it's like natural to just write those 6 lines of code. But I also do make this mistake quite often, and it's usually okay until stuff like this happens. Have you heard of the left path story? Yeah, probably most of you have, but there was a package on npm that was doing some like padding with spaces, and the creator of this package decided to pull it off from npm, and suddenly half of the internet broke because so many packages on npm was dependent on this package. And it was like 6 lines of code, so everybody could just do it by themselves, but I think we get lazy sometimes. And when we look at the languages that we write stuff today, if it's like C# or Java or Python on JavaScript, they don't really run on the actual machine. I mean, they run on it, but the code is not executed by CPU directly, because they're all sort of being interpreted or compiled into code that's used by a virtual machine, and this virtual machine gives it a lot of benefits and doesn't really run directly on CPU. So for example, for C# or .NET languages, it looks sort of like this. You have languages that have their own compilers, and they compile to like intermediate language, which looks sort of like the assembly but a bit different. And this code is run on a CLR, Common Language Runtime. And then this CLR is responsible for actually translating this code to the code that the CPU understands. This gives us some benefits. So you can't really crash the machine with using your code because it's all contained in the sandbox of the virtual machine. Your code is sort of protected. You cannot override other programs' code most of the time. You have automated memory management. You don't really have to think about freeing memory. You get garbage collector and so on. And it's relatively easy to do cross-platform with this stuff because you don't really have to write the code against the computer architecture you're running on. You just have to write the code that will run on the virtual machine, and there are different implementations of virtual machine that will run on Linux or Windows or different types of CPUs and so on. But this is not the code we run, so and it wasn't always like that. We used to write code that's much closer to the metal. For example, C. And my worst nightmare when writing C code was dealing with strings. So the way like strings are represented in memory of C language, or general like in CPUs, is an array, and you just get the pointer to the first element of this array, and you know the string is over because there's like null character at the end, like 0 character. So To get the length of the string, you just have to count all the letters until you get to the 0. There's of course functions for that, but to concatenate two strings, you have to get length of those two strings. You have to allocate memory that's big enough to fit those two strings, and you put the string into there. And then when you deal with it, for example, write it to the screen or to the database or wherever, you have to manually free that memory, because otherwise it's going to be taken by your object forever, and it's not going to be reusable, and your program will start leaking memory, because you just use more and more memory that's not really used, but it's allocated by your program. And the benefits are like pretty clear. You get a lot of performance, and you get a lot of control when writing your code. And in some places it's very important. So places like 3D graphics for games, and generally 3D graphics, they tend to be still written in C++. Even though the gap is getting smaller and smaller, it's always going to be faster because it's run directly on the CPU or on the GPU. A lot of physics models are also written in low-level languages. Most of the machine learning frameworks actually use C++ to run. You may use like Python frameworks, like with Keras or TensorFlow, but the actual calculations are done with C++. And also high-frequency trading, they tend to use those languages because they cannot afford the pause your program takes when you're garbage collecting, because quite often the trades happen so quick that this costs too much to take that break. And quite often in embedded software you just use C or C++ because there's like not much memory there. Although recently like you get like Raspberry Pi this size and you can run Windows on it, so we're getting into like different times these days. But there are still like software that, for example, runs in I once wrote a project for mines, and they have chargers for the lamps in the mines, and they were running on some really small CPU that you have just like 16 kilobytes memory there, and doing some logic for charging those batteries. So there are still usages where embedded software is a thing, and you read in really low-level code. But there are also a few modern approach to this low-level programming. There are new standard of C++ that also have smart pointers that kind of takes some of the work from you from magic memory. There's already garbage collector there. There are also two new languages, Rust and Go, that also get compiled straight to the machine code and have a lot of modern features. So it's not like it's a stuff of the past. There are still a lot of development in that area because there's still usage for this kind of code. But this is all still not the code that's like interpreted by your CPU. It still gets compiled. So let's talk about assembly. And to just simplify, I'm gonna talk about IA32, which is like Intel architecture that was using 30-bit systems. Now we're using the 64-bit extension of that system. I just decided to use IA32 for this talk because it's like much easier to present. There are like much less things happening there, but sort of principle stays. There's a lot of hardcore stuff going in the CPU development that's very interesting, and I encourage you to read on after that talk, but here we'll just get through some basics. So assembly is a code that's pretty much has a nearly one-to-one correlation of how your computer architecture is designed and how it's used memory and so on. There are no abstractions there. And let's look at like simple line of assembly code. This is like add EAX27. Add is the operation we're doing, and EAX and 27 are two parameters. 27 is just, in assembly code it's called immediate value, but something what we call like const, or and EAX is one of the registers. So what are registers? Registers are like pieces of memory inside CPU that are very, very fast. So 32-bit architecture of Intel had 8 registers, 6 of them general purpose and 2 other that's used for specific things. 64-bit extension has 128 of those registers, so it was like really hard to show it on one screen. That's like one of the reasons I decided to go with 32-bit here. And you can also see there are some legacy dependencies since the times we used like 16-bit processors and 8-bit processors, so you can still like address half of the registers. Register has 32 bits, so 4 bytes, but you can also, for the 4 first general purpose register, you can also address like the lower half of this register and the lower quarter of those registers. So for example, if you dealing with some smaller numbers, like you want to just save quickly one character on or a short integer, you can also fit this and reuse somehow the rest of this registry. Because there are so like not so many of them, you have to get really creative how to use them sometimes. So let's get back to this. This is also something your computer don't really understand. This is just more readable. So when it gets translated to binary, it will look something like that. And how do I know it will look like that? So when I started university, it wasn't that long ago, but Polish university tend to be still really heavy on basic electronics and computer architecture. My first assignment was to order those books. Those are like Intel reference for 32-bit assembly. Back in the day, like 10 years ago when I started university, you could just order them for free and you get like a huge box with those 6 books. I still have them on my shelf. So first of them was just general like rules how to deal with it. 2 of them next were just definition of the instructions. So there's a lot of instructions and a lot of parameters, and we'll just look at one of them later. And there was some optimizations guide and so on. Very, very interesting lecture. So let's look at just page of this that's define add procedure, and you can see there's like different sort of parameters you can get, but what we get, we use EAX as one of the parameters and immediate value. And you can see that because we use small numbers that both fit in 32 or 16 bits, it's gonna be the same instruction, and I also had to add 2 zeros there because I want to fill those 16 bits. And they're put in the opposite way you would normally write them. So first you put the least important bytes, and at the end they're the most important bytes. That's just convention is used. So let's look at example function written in a assembly. I'm using first line is a definition of what kind of instruction set you're gonna use. .386 is for 8386 processor. That was the first Intel processor that I had a 32-bit instruction set. So we're using just basic 32-bit instruction set. Those processors was clocked at 16 megahertz and 40 megahertz if you press turbo button. And so the beginning of this code is basically setting instruction set and defining what function we're gonna expose to external. So it's sort of like export in NPM packages. The rest of this code is a so-called code segment. There are different segments you use in assembly code. For example, you can have data segment if you define some local variables. This code just doesn't use any local variables, so we don't have data segment. We just define code segment when we write the actual contents of the library, because we can treat it sort of as a library. So here's like brackets for opening and closing. So there are some lines here like use 32 means we're using 32-bit instruction set. Assume CS code. This means that we're using this part of code, and also this line tells some instruction to the CPU how to interpret jumps, because jumps are sort of like a go-to in normal programming, and they can be interpreted both in a like very local and more wide context, and this is just like one of those information how to interpret it. And we're not gonna really dig into what does it mean right now. And this is the actual function code. This function called multiply. But first, let's look a bit at like calling convention, how you call functions using assembly. On the right stuff, I put a stack. Stack is kind of memory that's also used relatively close to the processor, and it's kind of you put stuff at the end of it, and you can just get stuff from the top of it also. But it's addressed like its addresses go down. So I just put it like beginning on the up, and if we add stuff to the stack and addresses go down, we just see that. And also, third operation you can do with stack, you can just take anything on the stack, just copy the value from it if you know the address of that value. So when you want to call function, you have to first push the parameters of your function on the stack, and you, in the CDCL convention that's used, for example, in Windows programming, you're putting the parameters from the right one to the left one, so from the last one to the first one. So first we put our second parameter of the function to the stack, then we push our first parameter, and then we can call function. So you know the site Stack Overflow probably. Have you ever had Stack Overflow error while programming? It quite often happens when you do recursion, because what happens, you call a function that within a function calls another function and so on. So what's happened, you just put a lot of things on the stack and never get them out. So if you go too deep with the recursion, you get Stack Overflow, because you fill so many data on the stack that it can't fit it anymore. So the more memory you have in computer, the bigger stack you have, but it always has some end to it. So now we call multiply, and it puts on the stack return address. So our function knows where to send back code when you finish with the code. And always when you call code, your responsibility as a person calling the function is to return stack to the previous value. So we're gonna have to set the pointer to the place of the stack that can be reused. This data will be still there, but it's gonna be not accessible anymore because the stack pointer will be like much above that. So let's get back to our function. So when you call the function, we're at this state. On the stack are already parameters we pushed when calling the function, and we also have a return address that we're gonna end at the end of the function, so we know where to get back to the normal execution of the code. And now we saving EBP. This is like the pointer as a base pointer, which you used to reference memory from the point you are. And as our base pointer, we're gonna use the current place on the stack. And from now on, we're not gonna use ESP as a pointer to the stack. We're gonna use EBP now. And now I want to start using registers to make some calculation. So I'll move is a value that copies value from the right side to the left side of the parameter. So first is destination, and second is the source. So we're copying value that's like 3 bytes up on the stack, which is parameter 2. We copy it to EAX value. The other register probably already have some value, because when you program on low-level programming, usually there is no 0 is not the default value. The default value is wherever it's in this piece of memory. So it's very important also to clear your variables when you declare them. It's like if you just declare integer equals C, there's gonna be some garbage in there. So if you want to have some results that you want to rely on, you probably want to put 0 there at the beginning or wherever it's your value. Now we used copy the other value to ECX. There's some reason why I picked this one. I'm just gonna show you another instruction. So now we have both parameters in a very fast memory, and now we can use function imul, which is a multiplication of 2 integers. And what imul does, it's multiply 2 32-bit integers, and sometimes when we multiply two 32-bit integers, you can get over 32 bits. It's gonna be a bigger number that fits into integer. So what this function does, it saves lower parts of the result in EAX and the higher in EBX, I think. So after this call, we're gonna have in EAX, we're gonna have the result of our multiplication, and EBX is gonna be probably 0 because the higher bytes of this multiplication will be 0. So now we're getting from the stack our base pointer again. That's gonna used for the entire code also, and now stack shows return value, and that's what's gonna use a function called ret use. It just jump to the memory that's implicated by the return address, and this is the address where we started calling our function. So again, pointer of instructions will get to the start of the function. And as we go, like on the left side you have EAP, which is instruction pointer. Each instruction is called in one cycle. So if your processor has 60 megahertz, it means it does 16,000 of those instructions. If your processor has 3.2 gigahertz, it does 3.2 millions of those operations in a second. And current processors not only have, for example, 4 cores, so they can run 4 instructions, but quite of them have also hyper-threading, which pretty much doubles the value. They have all logic to like figure out what can be run in parallel, and they try to put as much stuff parallelly combinations, so you get much faster calls. But back then, when we used like 386, there was only single-threaded one-core processors. All right, let's write some code again now in Visual Studio, because you can still write assembly in Visual Studio and debug it, so it's pretty cool. Yes, I do enjoy Visual Studio, but we're not gonna have this talk right now. Let's make it a bit bigger. So I made very simple entry point for the function, just to have some place to start. This is just a very simple C function. I define 2 variables, and then I call 2 functions, and just every program written in C has to have return value. If you return 0, it's okay. If you return something else, it means that there was some error going on. And I have some of this small library of math ASM. Yeah. And I wrote 2 functions here. One is like very dumb multiply, which I work pretty much like that I do loop, and if I, for example, want to multiply 3 by 5, I 5 times add 3 to some value. So it's like very dumb way to multiply, but I wanted to show you how loops work in assembly, because like, for me it's very interesting. So we actually just try to run this and debug this code, because why not? Just to see if it runs. Oops, wrong project. I set a breakpoint here, and now we're go inside the function. We're on our assembly function. So we do those things with the stack I showed you on the demo. We're not gonna delve into this. Can I make those bigger? But as you can see, I can put in watch the actual registers and see the value of them, and I get my values to ABX right now. I also put 0 to EDX to have some place to accumulate the values. And now we have start here, which is sort of label. And this is just another instruction that's only you remember the instruction address of this thing, and we're gonna use it later to get back to this place. And right now we're adding EDX to AAX, and they're gonna be accumulated in the first one, so EDX. So we get 3 here, and we're gonna do it 7 times because we're multiplying 3 by 7. And now I'm also decreasing EBX, so how many times I want to actually loop these things. And this is very interesting part. G and Z means jump if not 0. So, and it also works in a context. So the last change register of ABX, so this will actually apply to the last change register, which is ABX. So if we're not equal 0, if EBX is not equal 0, we're gonna go to point that was marked as start. So we basically just remove the instruction pointer back to the address where the start was. So as you can see, the natural way for CPU is actually use goto. But don't use goto in your code, it's just bad practice. But you can see that's how actually computers do it and how compilers do it for you later. So now the next step, we'll just put that back again in this loop, and we'll just loop multiple times. And now EDX has varied 21, so what basically multiplying 3 by 7. By convention, the return value is always in EAX register, so we now have to copy this value to EAX register. So that's here. And now we do the whole magic with the stack I showed before, and we're returning the value that's in EAX and get to our address. So now I can see that dump product is 21, so what we expected. Now I have another function which is like smart multiply, which is the actual how CPU does multiply, and this is the function I showed you on the slide, the one what we kind of stepped through. So this is just one instruction. So the other one took like 21 CPU cycles because we went all through 7 times doing 3 instructions, and this one just took 1 instruction. So we just optimize it 21 times faster, and the result is the same. That's cool. So I also wondered if, like, I now called assembly code from C. I wonder if I call this code from C#. So I made library, and I just built library into DLL, and then I wrote C# code that uses this library. And what I'm using here is called platform invoke or pinvoke. So you can use native code from your .NET applications. And you can also mention that I have to put a calling convention I'm using here because you can use different, but CDCL is the one that's most commonly used. And I just have to define this function as extern, so then IntelliSense can use it and compiler can use it. And it sort of assumes that this function is here. It doesn't check it during compile time. So if it's actually wouldn't be there, it will get runtime error. But I hope it will work for us. Yeah, and my library has actually something else. Like if you were to my talk yesterday, you saw that like AX plus B is like stuff like basic machine learning or basically linear function. So now my API use a multiply I wrote in assembly to multiply, so it's faster. But in reality, like sometimes people write assembly to go faster, but most of the time you're gonna get never better than what compiler does. So it's probably you can write assembly for fun, but you probably not get better performance than your compiler. And then I use this multiply product and just add another value to it. So basically have AX plus B function. So I'm just using it, and the result should be like 3 times 5 plus 7, so 15, 22. So let's just run it. Result is 22. No, it's 122. I know why. Because in my assembly, when I did this presentation previously, I just did this to just prove that it actually does what it does. So let's just remove that code and rebuild the library and see if it's actually I'm using the same assembly code. So with Visual Studio, sometimes it fails to notice changes in assembly and don't rebuild them. So the trick I found what to do is just change the target CPU, build it, and just get back to any CPU. and build, rebuild or whatever. So now I'm gonna run this CS program again and see if it's gonna be 1022 as I did, or just the actual value that it's supposed to be. So yeah, now it's 22. So we also have a proof that I actually used the assembly code that's written in a library to call from C# to so on. But when you call that code from even higher level, for example JavaScript, and for me it was just the easier step, because the natural way to use C# code from JavaScript is just doing Ajax call. So that's what I did in another project, just for fun. So I wrote very simple application in Nancy. Nancy is very simple framework for writing web applications, and I have 2 endpoints. One is that kind of returns the website that I'm gonna use to values, and second was like API that calls the AXB function that calls our library in assembly and responds everything as JSON. Yeah, so let's put some values here and see how it goes. This should be result 52. And it's also actually using the assembly code for multiplication. So I find it pretty cool that even we write really modern stuff in JavaScript, in the end it's also get called and calculated somehow on your processor, and you also can really use those low-level functions to do some stuff. So even though we really do like high, very untouched stuff from the CPU, we sort of stand on the shoulders of giant, and it's all been layered by the years and years of work and making this easier. So at the beginning, people were programming with zeros and ones, putting punch cards. Then they decided like assembly code that's sort of easier to understand for human. Then we wrote languages, high-level languages like C, that we compile to this assembly that then gets run on CPU. Then we started building virtual machines that kind of shield us from some things that are uncomfortable when running the code, like manual memory management and so on. But it's still at the end of the day gonna get called on the metal on the CPU. Worth mentioning that EA32 or 64-bit extension for that are not the only architecture. EA32 is like the classic example of CI/CST, so it's complex instruction set computer, because it has like those 2 books of instructions different. But there's also a completely different idea, which is called reduced instruction set computers that have just few instructions that they're designed to moving stuff between registers, but they have like hundreds of registers using different things. A lot of things are just used by convention there. And classical RISC architectures are, for example, ARM, that use in most of your mobile phones. Atmel AVR, which is used in Arduino, or Motorola 680K, which is used in most of like radios and also a lot of network switches and so on. So yeah, thank you for coming to this talk. I put some links and also some instructions how to set up Visual Studio for doing assembly writing. I'm also gonna tweet this link. If you want to dig more into this topic, that's amazing book that just starts about like zeros and ones and just go all the way up to the way computers work, and do it in much more details than I could get in 1 hour. It's fantastic book if you're like a programmer and really interested how computers work. And also, a sort of related topic is the WebAssembly. That's allows you from JavaScript call other things that get compiled to assembly that's understood by browsers. And Bojan will have a talk about it at 1:15 room 3. So if you're sort of interested in that topic, you should also look into this. And cool, I can take questions now if you have some.
there are some. There are some operations in assembly that are useful for for searching in a strings or concatenating string and so on. I've seen the guy that write, for instance, better concat, and this is the reason why we may use assembly in a .NET application.
Yeah, sure.
Or other managed.
Yeah, there are definitely legitimate reasons to use assembly. That's why we still can do it. But for most of the programming work, you're probably not gonna get any gains. There are also like very cool instruction sets that, for example, deal with that are very good designed for doing with tabular data, because they, for example, process like 8 pieces of data with the same instruction multiple times. So they're very used for multiplying computers. And also that's how GPUs work, but they just have, for example, 128 multiple things. So they can just, you know, like do very quick matrix multiplication, which is used in changing the view in 3D graphics and so on. So yeah, there's definitely really cool stuff, and with the modern architecture, some of those instruction sets are really crazy, and it's like really interesting to delve into this and see what's happening there if you're interested, of course. Any more questions? Cool. I have some t-shirts here, as yesterday. The one with the white label are ladies' feet, the other with the black label are male feet. Feel free to take them. We also have a lanyard that also can work as a beer opener, very useful. So feel free to take it, and have a nice rest of the day. Thank you.